Okay, yes, this is my homework assignment for today to talk about the computational data science challenges. This is my homework 15 turned in. So I took Anne Cristiano's talk yesterday to heart and really listened to her perspective on it. They have to tell a story. They have to make sure that the story doesn't stop. So I definitely tried to do that. So there's a story process, but to make sure it didn't suck, it's not my story. I stole somebody else's story. This is the Dr. Seuss version of this. And the other reason to use Dr. Seuss is because yesterday, not only was it National Burger Day, but it was also the day that Governor Arnold Schwarzenegger awarded Dr. Seuss with the California Hall of Fame medal. So I think Dr. Seuss should get at least as much respect as burgers. Make sure that happens. All right. So I'm going to talk about challenges, computational and data science in biodiversity. My big thing that I'm focusing on now is helping build long-term global monitoring systems that have impactful outputs. That's kind of the theme of what I'm doing, and we'll see that coming through this a little bit. Okay, so first thing, core data, rich data. Whose data, which data? General one fish, two fish, red fish, blue fish. Core data, rich data. Okay. This is challenges in data collection, availability, data licensing, and data discovery. This is a topic that I'm ad nauseum about. I'm just going to focus on just the data collection cycle. Quick. As we all know, there's tons of data, more data all the time. We're washing data. This is the amount of structured and unstructured data. This is an expectation for 2020. This is exabytes of data, so billions of gigabytes of data coming in all different sources. What's really interesting about this chart is when we break through 100,000 here, we're going to exceed a yottabyte of data. Right? And what's extra interesting about exceeding a yottabyte of data is that's as far as we go. Like, we got kilobytes, megabytes, gigabytes, terabytes, petabytes, exabytes. Now we're going to zettabyte, yottabyte. There's nothing else, right? So what happens when we go to the limit? We're going to have a contest, and it's going to be like database or something like that. You should get your votes in now for what the next level of height is. So in biodiversity, we also have a lot of data. I know what percentage of the yottabytes biodiversity data versus a lot. One challenge with biodiversity is there's a lot of things you can mean by biodiversity data. These are the IT targets for the Convention on Biological Diversity. And you look at these things and try to figure out what metrics are used to measure each of them. It goes like understand value, right? Like, how do you measure whether people understand the value of biodiversity? Well, it's not like measuring, abundance of some species or something like that. Actually, most of these are of that sort. It's like there's biology in there, but there's a lot of other data that people are collecting that are related to biodiversity, but aren't necessarily specifically biodiversity. And even if you look at things like half the rate of loss, this is actually half the rate of loss of habitats, rather than half the rate of loss of population or something like that. So one of the challenges with biodiversity data, as you all know, is it's just hard to get the source data, right? You're always using surrogates and things like that. And there's a lot of it. So I'm going to focus on just like observation data for a second. So here's GBIF. GBIF aggregates occurrence records. So there are over 1 trillion occurrence records now. This comes from lots of different sources. They're doing a pretty good job of bringing data together and making it available. I think it's a good model, and it's interesting to think about like data, types of data, and can we have GBIFs reach different types of data? So GBIF is a good model for sharing observation data and networking it. There's like trace data. It would be interesting. It would be nice to have just a list of different databases and data sources. One thing with all these data is it's really different. Oh, I see. Okay, here we go. Okay, so this is the GBIF data. Now, if you look at over time, where all the observations happen, this is the distribution. There's some interesting things like You know, okay. So here the like bias is clear, right? It's not like biodiversity in Europe and U.S. and Australia is higher than biodiversity, you know, here in the middle of South America, right? This is just where the data happens collected. The bias is getting better over time. So this is, GBIF has this cool tool where you can see data collected older data, and this is from the first 100 years, so from 1600 to 1700. Okay, so you can see actually like bias kind of persists, but the story is getting better. One thing that's interesting about the GBIF data is the largest source of incoming data now is camera tracking data. So that's in terms of the quickness increasing, the highest velocity of data is through camera trap data. And so so that's good and interesting. And I like camera trap data because you can set up camera traps and leave them for a while and collect data over time. So when I think about these sort of long-term monitoring platforms, like having a set of cameras that are collecting data over time for a long time, giving you a continuous record is something that I like. And so one of the things that I'm working on is this thing called Wildlife Insights. So Wildlife Insights is a collaboration of a bunch of NGOs, so Conservation International, WWF, WCS, Smithsonian, a bunch of others, and Google are all getting together to build a camera trap data aggregation platform. And so the idea is all of those groups that have millions and millions of camera trap images are going to be bringing them all together on this platform. And then people who want to upload their own can do it. And built into the system is a machine learning algorithm that identifies species as you upload them. And maybe even more importantly, well, recognizing species is cool, but it also recognizes plants, which is like sometimes 90% of images that come from a camera trap are like leaves blowing in the wind or something like that. And you're sitting there like the jaguar, the puppy, right? So the idea is wildlife insights will like clear out all the leaves, but keep all the species. The other thing that's interesting about camera trap data is often the camera traps are set up to stay a specific species. You'll have snow leopard camera traps, and the people who are using that throw out all other data. They don't care about it. All I care about is snow leopard, like you're eating links or whatever they're interested in. But this system's going to capture all of that stuff as long as you can actually do files and identify as many of the species as possible and aggregate it so that and they get public. So once this thing is live, which hopefully will be this year sometime, people will be able to go to the site and analyze all the local camera trap data that have been aggregated so far. Next topic. Some have 2 cores, some have 4, some have 6 cores, and some have more. Challenges in processing. The cores here is like core content, signal processing. So, you know, machine computers, CPUs just have 1 core processing. 2, now you get CPUs with tons of cores that all work together. What do you do about that? All right. So here's some fun facts. This is the annual additions to computing power in exaflops. Okay, so a flop is a floating point operation per second, and this is the the whole globe access to computing power, and like pretty flat, pretty flat, pretty flat. This is when cloud computing started to become a thing, and virtualization became a thing where you can have virtual machines running on multiple machines, and you can just see that the amount of computing power that's available to everybody is just humongous, and it's a relatively new thing. Right? This is end of 2014. It's still going up. So there's lots of computational power that's available now. The question is how can we use it? One thing that's nice about technology in general is it gets cheaper over time. So now with cloud computing, you can, if you're setting up your laptop and you're trying to do something that's RAM bound, memory bound, you can go to the cloud and use a machine on the cloud, and you can get some enormous machines, right? So I'm just comparing Google and Amazon, or you can compare, or actually they're not comparable, but You can see here that you can get machines that have 96 cores. Ridiculous. And 360, 348 gigs of RAM. So if you're having problems fitting a process on your laptop, you can rent one of these machines. It costs $4 an hour, $4.50. Or if you get one of these ones where it kind of runs when it can and you're not in full control over the timing, you can get it down to $1 an hour for one of these huge machines. So that's pretty cool. There are also lots of smaller machines, like 1 core, 4 gigabyte RAM machines that you can actually get for a penny an hour, right? And these are really no better than your laptop, but the thing is you can get a lot of them. You can get them to like all of the other tabs. If you don't want to spend any money, there are also alternatives that are free. So Jetstream is one. You go here, Jetstream Cloud, I think is the URL. And for research, you get a virtual machine there. NASA has the NEX program. You have to apply for it, but you can get access to the supercomputer. You've got your computer clusters wherever you are. Many universities have them. If you're doing geospatial analysis, you can use Earth Engine, which is free, and it's designed to run very large geospatial analyses. So it has petabytes of satellite data and lots of other data, and you can run your own algorithms on it. And the thing that's interesting about Earth Engine is all the parallelizing happens under the hood, so you don't have to know how to parallelize any of your operations. The idea with parallelizing is if your problem is really big and you're able to cut it up into little bits, you can send those little bits to different machines, have those different machines process it, and then bring it together and get the results. And that's how you leverage all these little machines that you have available in the cloud. To give you a sense for that, one of the things that I've worked on was with Matt Hansen at University of Maryland, who in 2013 did an analysis of forests for tree cover change over time. So this was a global 30-meter resolution map of tree cover change over time. We're showing loss and gain. And here it shows sort of the year that it happened. Red is more recent change. And you can zoom in, anywhere on the planet and see what the forest is doing there. This was a pretty big run, so, and this we did in 2012. So it was almost a petabyte of data and a million hours of computation, but it was spread out over 10,000 CPUs. And so you were able to run and take 1 million hours. It took about 4 days, which is pretty good. And now Matt's running this on his own hardware now, because we've got it available, and it's probably a lot faster now than we can do that as well. But that gives you an idea of the scale of things you can do when you parallelize. Now, here's some challenges in parallelization. One is saying parallelization. Practice that at home. There are a couple of rules. So talking about computer science laws, these are things in computer science called laws. One is AMDAHL'S law. Basically says that the amount that you can speed up a process through parallel processing is kind of proportional to how much of that process you can parallelize. So if you take a process and break it up into different amounts and parallelize parts of it, you can speed them up to a certain degree, and this is a good formula for how to do it. So the basic idea is like, I got these from John Christian Meyer. Like let's say you are, your job is to clean people's houses or go on, and you go an hour to get to the location, and it takes you 9 hours to do it. Altogether, it's going to take you however long that is to do it. But if you have friends who can help you, you can divide the task up, and it takes less time. And if you have more friends, it takes even less time. But the thing that's interesting about AMDAHL'S law, which tells you like how much more efficient your process gets as you parallelize it, is this little bit, the part about getting to the spot, never changes. You can't parallelize the drive from where you are to where you're going. You can't. It takes as long as it does. There's a limit to how much how much benefit you get, and eventually you can throw more and more CPUs at this, or more friends. It's always going to take at least an hour. So that's one kind of interesting thing about Untitled. Now, people who are using it, it's very useful, but realize that in practice, when you're doing computer science projects, when you're optimizing, often what happens is you're not just trying to make a process faster. What happens is as soon as you start making the process faster, you start throwing more data at it, and it's like immediate. So here you are visually optimizing your algorithm, and then everybody who's using this thing, more data, more data, more data. And in the end, things takes as much as long as it did before. It's just you can do more. And in that case, Untitled law doesn't really apply because Untitled law assumes a fixed workload. Luckily, there's a new law, the GUSTAFSON'S law, which works in this mode of workloads rather than time. So following the same sweeping thing, it takes you that long to do it yourself. And if you have a friend, you can do twice as much, except for the amount that's here, which you can't really save on that. So that's GUSTAFSON'S law. There's another way of parallel that. And more friends means more work. And the moral of the story is that you give more resources, people don't do what they were doing before faster, they start doing newer, bigger things. Right? So if you want to get the engineers in your department excited, you start talking about the size of the data that you're going to give them, and then they start thinking like, oh, how are we going to do that in so much data? If you're doing it faster, that's back in Untitled law day. All right, next chapter. Some are high, some are fast, some are slow, some are high, some are low. Some are drivers, some genetic composition, some are populations, the same eco function. Okay. See, I'm starting to scratch it here. All right, this is challenges and scales and output. Actually, when I think about scales and interoperability, I think it's a little bit different than what we're talking about here. When I'm thinking about scales, I'm thinking about different processing modalities in a way. And in the stuff that I've been doing, there seems to be kind of two realms. There's the realm of direct observation and measurement, and then there's the realm of modeling. And modeling is its own universe with its own algorithms and processes and issues, and then direct measurement from in situ data, satellite data, a whole other thing. But they should really be working together. They tend to operate at different scales. One is operating on species populations, abundances, richness. The other one often applies to drivers of change, or socio-ecological levels. So how do you combine that? Here's an example of one way you can combine them that I'm thinking about. There's a system called INVEST, which is at Stanford. It's way
and University.
Yay! It's a way of measuring existing services, and it's a lot of models. And one of the models is this sort of scenario planner, and takes inputs like this or like this, where you say, oh, there's a certain chance that forest is going to change, and it's going to most likely change agriculture, maybe shrubs, woodland, or urban. 10% chance that woodland's going to change, and likely change the shrubs or urban. And through expert consultation, these matrices are created and entered as complete things that are coming out of these meetings. Similarly, these rules, it's the same thing. But the interesting thing I'm thinking about is like how much of this could you actually directly measure, right? Like if you had a long enough span of time and you could measure the change of land cover, like could you generate this automatically from data that you have, and then help build a scenario planner so that it just was constantly rolling as you're bringing in more data, hopefully from long-term systems. So that's kind of a fun task. And others are too. There have been sort of recent papers on this, so this is a kind of cool one showing from local place-based to global generalized and social to biophysical. We're talking about the different kinds of studies you can do here, where the breakdowns are, and where the opportunities to bridge across scales are. And so it's an interesting line of work, and I think moving forward here is how do you put machine learning into these more sort of flow-based models, and so there are a bunch of different things to do. So this is kind of interesting work. In computer science, one place that we see scales, one place to see scales is the internet. So this is what's called like internet stack, and it goes from like coaxial cable or twisted pair cable to Ethernet cards in your machines that can talk to each other, to this internet protocol, which is how machines send information to other machines and other networks, to these things, transport protocols, which tell you how to put together information again, to the next level, which is like HTTP, the World Wide Web, which is more about how to display the data and we use access it all the way up to like a browser and other applications that use all this information. And these things all stack up, right? This is a really interesting version of scale. You're going, from really like physical level, get more and more, abstract, so you get this high level complexity here, which is these applications that sit on top of all this. And in each level, there's really good specifications for how to pass information from one level to the next level. This is a kind of fun study which is looking at like, why is it like this? Like, why is the internet protocol here not the only one that's in the middle of these ones that branch out here? And we talk about this. That's something cute. In the natural world, species that share the same ecosystem often compete for resources, resulting in the extinction of weaker competitors. A new computer model that describes the evolution of the internet's architecture suggests something similar has happened among the layers of protocols that have survived and become extinct on the worldwide network. So you know it, but your work here is being applied to the evolution of the technosphere, in which we are all embedded. All these protocols are created by this group called the Internet. What is this now? The Internet Engineering Task Force, and they put out these descriptions of how these things work. And then there's this really cool document which is called Some Internet Architectural Guidelines and Philosophy from the Internet Engineering Task Force. And one of the things I really like about this is it gives you a lot of really interesting information on how to scale, how to work across scales. So it outlines the philosophical guidelines, which architects and designers of the internet should adhere, including the simplicity principle, which says keep it simple, stupid, and lots of other very scientific kinds of edicts. And one of my favorite sentences is this. So this gets back to Angus Gano's use of visual language. It's always possible to agglutinate multiple separate problems in a single complex interdependent solution. In most cases, this is a bad idea. Thank you. No agglutination for you. All right, the last chapter. Hello, are you there? Hello. I called you up to say hello. I said, hello, you hear me, Joe? Oh no, I cannot hear your call. I cannot hear your call at all. Not good. I know why. I'm out. Cut the wire. Goodbye. Challenges in communication. All right. So back to this global forest change or tree cover change data set. This is a full data set. It's a GeoTIFF. When we worked with Hansen on the first version of it and released it on the website where it's at and could be downloaded. But the next thing that happened was the World Resources Institute created Global Forest Watch. Oh, now it's called Global Forest Watch. This is cool. The Global Forest Watch, which is a site that aggregates forest data. And they're an NGO and they have lots of connections to governments and industry and civil society groups. And they tried to bring the data together in a way that made it easy to communicate. And so one of the things they put in there was Matt Hansen's data. And so you can go to the site, go to Forest Watch, you can look at his data, other data, you can do simple analyses like circle an area, and find the gain and loss of the area. And it was very useful. So just having this sort of NGO take the data and put it in this operational system with lots of context, have like stories. They made a deal with some with Manga Bay to have Manga Bay do stories that were related to it. They worked directly with governments to show them the tool and to use it. It actually drove policy change. So there have been government national level laws that have been put in place based on results that were surfaced through this platform. They were not created by the World Resources Institute. The World Resources Institute created this thing to get the message out. One thing that, so this ran for a long time and was super useful, but at some point, WRI decided they wanted to impact industry, in particular palm oil plantation owners. And so they're trying to figure out how to use global forest watch to get palm oil plantation owners to stop cutting down primary forests to plant their palm oil. And they would show them the maps and say, here, we can show you where all this, all fires are impacting you, where illegal logging is happening, close to your territory, you didn't do that. And I went to these meetings and like over and over, the people in the industry were saying like, I can't deal with that. What is this? Lots of pink dots, thank you very much. And they were just constantly frustrated because they couldn't act on the information. So then WRI went into this multi-year effort to try to work with the companies specifically to get information into the form that they could use it. And so they created this thing called Global Forest Watch Pro, which is for bankers, producers, commodity traders, and consumer goods manufacturers. And it takes the information, mixes in the company's information, and generates reports in exactly the form that we want that they can then act on. So now companies are getting on this thing and starting to use it, and it's a way of driving impact. Another example of sort of industry using science to have impact is this thing called the Science-Based Targets. It's called Science-Based Targets Network. And this is, right now it's up to 554 companies who are making commitments to reduce their carbon emissions. And they have a whole protocol for making these commitments and monitoring them and how to make sure that they're reasonable. And this is all driven by industry. So while government is fooling around with sustainable development goals and those other kinds of indices under there, industry is going ahead at least on the climate front and making their own targets. They want to do this in biodiversity, but they don't have anything like carbon emissions. Right? Like carbon emissions is an easy thing to get your head around. I'm going to cut my carbon emissions. I'm going to measure my carbon emissions. I'm going to cut that. That's pretty straightforward. But when you talk about biodiversity data, there's no equivalent right now. So this is the challenge for action. What's the equivalent that industry can do? So one of the things I'm thinking about a lot is this process of how to take data, transform it into information that's actionable and decisionable, where you can decide, make decisions about it. And so the group's doing that. One I just started finding out about is this Biodecisions Alliance. The thing that interests me, so this is, well, what interests me is this, especially in the context of this group, where it says, they bring this together, experts in conservation, mathematics, systems modeling, social science, political science, computer science, and environmental policy. Now, I don't see evolutionary biology or like genetics in here, which is just silly, and it ought to be. And so, I'm looking forward to looking at them and doing some of this we're talking about here. It's that. All right. And now, good night. It's time to sleep. We will sleep. We want to sleep. Today is gone. Today was fun. Tomorrow is another one. This talk is done. This talk is fun. Another one. Thanks very much. Question time, or can you still write the challenge? Okay. All right. And are we going to break here? Yes. Here are my challenge questions. I'll do that. Yeah, and so we'll have like 5 post-its you can gather around. So the first one is data management challenge. What hideous data processing task do you find yourself doing over and over that could be automated if someone just spent the time? Because this is our driving, when we built our engine, this is our driving target. was we wanted to like reduce the 90% of silly stuff that we're doing, downloading data, reprojecting data, all that kind of data management stuff that kept you from doing science. We wanted to automate it. That's what we built our venture around. That's how we measured our success. How many silly hideous data processing tasks can just be handled. So that's the first one. Interoperability challenge. So please gather around and find one multi-scale problem that uses 2 or more disparate data sets that need to be combined automatically. And what's the challenge there? Just think one, like a very crisp problem that uses 2 known data sets that are a pain in the neck to combine or more data sets. And why is that hard? Oh, we're doing the same tweet thing, right? Somehow in a tweet, right? Computational challenge. What is one common computational bottleneck that you encounter that you think could be addressed through parallelization? Global diversity monitoring system challenge. What are 3 specific outputs that a global biodiversity monitoring system should provide, and what would be a sort of useful cadence, like update time to provide that? Some things only needed every year, some things might want to do 2 minutes. What are the 3 biggest outputs that one like such a thing could give that would be useful? And then the last one is capacity building. What are 3 technical tools you wish you knew or understood, but can't wrap your mind around? Questions?